Guys, in this video we're going to take a look at the example of some coordinate transformation on the cotangent bundle. And the reason why we do this is because it's pertaining to the Hamiltonian formulation of the classical physics. So here again, I'm switching the notation here. Instead of having P as a point on M, I'm gonna let X be a point on M, and let P is going to be the momentum conjugate on this cotangent bundle. Okay, again, the basis for this is dxi here. This is the basis for the covectors. So recall, whenever you have the coordinate transformation at the manifold level, like xi to xi prime, this will induces a change of coordinates on the cotangent bundle. So the cotangent bundle is just the T and then the star and then the M. That's how we define it from the previous video. And notice the indices of the P. The P is downstairs because the basis is upstairs. The dxi is upstairs. So therefore, the P itself is a covector. It's a form, one form. Okay, and the transformation is the following. This is on the cotangent bundle. Xi go to xi prime, and then Pi go to, since the index is downstairs, you're gonna have that Jacobian in that particular order, and then you have the Pj downstairs to the right. And of course the partial xj, partial xi prime is an inverse Jacobian opposite to the one that we use for the tangent bundles. Okay. Okay, so here is the proposition that we want to prove without loss of generality. We're going to let n equal to 2, so it'll be easier. And along with the induced chart, phi alpha hat and phi beta hat, give us the transition map between the two coordinates that you see there. Okay, and then we're supposed to prove the following. Then px and py is equal to the following here, as you can see, and then pr and p theta is right here. It's very similar to the way I did it for the tangent bundles. Okay. All right. Here's the proof. So all we need to show is this: the covector pi dxi is equal to some new components, pi prime dxi prime, which is where dxi prime is a new basis. If we can show that, I mean we're done. Okay. So let's see how the pi transform. Where the pi, the index is downstairs, so it transformed like the basis for the tangent in the tangent bundles. So the prime is going to go downstairs. Okay. So we're going to use this formula to get our transformation into the new coordinate systems. So for example, P1 prime is going to be Px. And so according to the formula, it's going to be Pxj to P1 prime, but P1 prime is Px, so therefore it's going to be like that. And then of course J is going to go from R to theta. Okay, so P of x1, which is R, P of x, and then PR plus P of theta r p theta. Okay, so we just have to take the two derivatives. So that's just gonna give me 1/2, and then times 2x, so that will give me x over r, so that'd be a cosine theta times pr, and then p theta px is gonna be 1 plus y squared over x squared, and then dy over dx by dx. So that's going to pick up a minus sign, and then that term is going to get multiplied by a p of theta. Alright, so simplifies. This is going to be x over square root of x squared plus y squared. So that's just r. So x over r is just a cosine of theta. And then over here it's going to be minus. Pick up a minus sign, so minus y squared over, no, minus y over x squared. So then I have a y over x r squared, so y over r would be sine, so it would be minus sine over r times p theta. So that's px. So let's call this equation 1. And use that formula again. P this time it's going to be py. So partial r partial y py pr, and then plus partial theta partial y p theta. Again, let me just write down r so I don't forget. R is equal to this, and then theta is equal to arctan times y over x. So this here would just give me y over r, so that is just sine theta times p of r. And then 1 over plus y squared over x squared. And then, so this just give you 1 over x. So this here is just cosine over r. Yeah, the second term here just give you x over r squared, so that is cosine over r. Cosine So P sub y is equal to sine theta PR plus cosine over R P theta. So the only thing we need to do is just expand, expand the dx and the dy. So px is pr dr plus p theta d theta. If we can show that, then we're done. Okay. So let's start with the left hand side here. Plug in for what? Px dx, py dy. So px is cosine theta pr minus sine theta over r p theta. And then of course dx is you have to expand that. So dx is equal to cosine theta dr minus r sine theta d theta. And you do the same thing for the py and dy. So py is sine theta pr plus cosine over r times p theta over r p theta times dy. So dy is just sine theta dr, and then plus r cosine theta d theta. And then what we need to do now is just multiply this out and see if it gives us what we want on the right hand side of that previous equation that we wrote down. Okay. So expand this. So cosine square PR, put PR in the front, times dr. That's the first term. And then you have the second term minus RPR cosine theta sine theta. Put the PR, I put the PR first. And then the third term is sine theta cosine theta p theta sine theta cosine theta, and then over r dr. And then the last term for the top term is going to be plus sine square p theta and then d theta. Expand the bottom. The bottom is sine square PR dr. And then the cross term, so I have r PR sine theta cosine theta, and then d theta. And then the third term, cosine p theta, p theta cosine theta sine theta over r dr. And then the last term is the r cancels, so you get p theta cosine theta square d theta. And you see it's going to be many cancellations, and what we will end up with is just exactly PR dr plus p theta d theta, and we're done. And that's how your covectors is defined on this cotangent bundle. Okay. And of course, the acceleration was just one step up. So second tangent bundle to this will give us the acceleration. And there you go. In proof. Done.